This is lecture number 15. In this lecture, we are going to discuss single and multi-loop feedback control method. Today, we are going to cover conventional negative feedback control, then link with voltage feedback control in switch mode power converter, then PWM voltage mode control, which is a single loop feedback control, is a very well known method. Then we are going to talk about PWM current mode control, which is a two loop feedback control. And finally, I want to discuss some advantage and limitation of this multi-loop and single loop feedback control methods. So, first I want to show the overall block diagram of the feedback and feed forward control method, and we have already discussed that in this method we need a sensing circuit like a sensor. Generally, this include a feedback sensor like a resistive voltage divider. Then we can also consider one unity gain buffer circuit and so on. And then the feedback control method, which include error amplifier, compensator, and also the control logic, what control logic we are going to consider. And in this lecture, we are going to discuss like the series of lecture, first fixed frequency control, then variable frequency control. So, this structure will differ based on what control logic we are going to discuss. This next part is the modulation technique, and this we have already discussed in week 2 series, where we talk about fixed frequency modulation, variable frequency modulation. So, even though the feedback control structure may be same, the modulation can be different, and as a result the the stability and other condition can be fundamentally different, and those things we have already discussed. So, now we want to take one by one different control method. What are the objectives in this control design or in the feedback control? The first, our system should be well damped and it should offer fast transient. Second, it should have a good disturbance rejection. In fact, we saw in the previous class that feed forward control, which can substantially reduce the effect due to the input voltage variation, the effect due to the load current variation. So, this technique can also be incorporated for disturbance rejection, but without feed forward, feedback can also reject disturbance, but I mean it has some limitation, because we also discussed that it takes time to respond to the disturbance. So, feed forward action can speed up. We also want to achieve very tight voltage regulation, and this is where the feedback control play a significant role, because you can have parameter uncertainty, we can have disturbance, we can have component tolerance like component variation, edging effect, but in spite of that we need to regulate the output voltage and in some cases also output current, like depending upon the application. And finally, I will also discuss today's class that how if you turn off the power of the power supply or the converter, that means that is called a startup process. That means everything starts from 0, the voltage and current starts from 0. So, if you suddenly enable the feedback control logic from the very beginning, then what can happen? I mean what could be the overshoot and undershoot of the current and voltage, that also we need to discuss. And then we also want to discuss some of the soft start technique, which can smoothly transfer the voltage to its desired value in spite of the feedback loop being activated. Okay. So, in single loop feedback control, if we take a typical like a traditional control feedback control. So, generally we have a sensor which sense that what signal we are going to take the feedback. In some cases, in most of the cases in power supply, we need to sense the output voltage, because we want to regulate the voltage. Then this goes to, there will be a reference signal. So, this reference can be voltage if it is a voltage regulator. If it is a current regulator, this can be a current reference, and we need to sense the current, which current we want to control. In some cases we want to control the inductor current, in some cases we want to control the load current. Then there will be a controller, the error voltage or the error signal, irrespective of whether it is a voltage or current. Then the controller, what type of controller it is, like a standard controller we know about, proportional, integral, derivative, lag lead compensator. Then this controller output will go to the actuator, okay, and this actuator actually go to the plant. So, in power converter we will find these actuators are nothing but the controller is implemented using kind of op amp, but the actuators are typically driver circuit which try to, because whatever gate signal we generate in terms of modulator, this include modulator like and driver latch. So, ultimately that signal should turn on and off a switching circuit. That means, it should have sufficient current to turn on the switch within a reasonably small time, that require a driver circuit. This is because it has to turn on and turn off power MOSFETs, power devices. So, the sources of disturbance we have discussed. In typical control system, the disturbance can occur after this actuator output. It can also happen like part of the process, and the noise actually occur at the measurement point. That means, we are trying to sense the output voltage and this noise can propagate. So, there are that noise can happen, this noise can be like a white Gaussian noise, but in spite of this noise and disturbance we have to design the controller or the compensator. We want to link this single loop because it has only one feedback loop, and whether it is a voltage loop or current loop, that we will discuss. Single feedback loop, and if we want to relate this with our switch mode power converter, then if we take a voltage feedback, that means this is the output voltage coming out of this converter, and this output voltage is sensed, and actually this H, the feedback gain, this may include the resistive divider. Okay. So, this is the measured voltage and this is compared with our reference signal, and then we generate the error voltage, and then we implement a controller, and generally an op amp is used to implement controller. That means, depending upon whether we have to implement type 2, type 3, PID, PI. So, the number of op amps will vary. In general, one op amp may be sufficient, but the op amp has a supply, finite supply rail. That means, it has a, whether it is a dual supply rail or it is a unipolar op amp, depending upon that there can be a saturation nonlinearity. That means, we cannot increase the gain of the compensator which can saturate the output of the op amp, and this saturation can cause some nonlinear effect which cannot be captured by a linear analysis. Okay. Then controller output goes to a feedback controller, feedback modulator block, PWM modulator block. In case of fixed frequency, this modulator is a like a fixed switching frequency, and it generates the gate signal with a certain duty ratio. Okay. And this duty ratio, if we try to derive the small signal model, this control to output transfer function is this one. Then there can be disturbance in the input voltage which will be affected, and which can affect the output voltage. There can be disturbance in the load current which can affect through this output impedance. So, all these actually add up to generate the output voltage. So, any disturbance either in input voltage, load current or duty ratio can cause disturbance in the output voltage, and that comes to the feedback loop, and then feedback controller takes the action. So, in case of voltage mode control, the output feedback, as we discussed, it is a voltage, this is the output voltage, and this could be a resistive divider. That means, we can simply consider a resistive divider path. That means, this can be the actual output voltage, and we can tap this. This is my feedback voltage. Okay. This is my actual voltage, and we can put a R, R1, R2, and this Kf, which is the feedback gain, is simply R2 by R1 plus R2. R2. Okay. But we need to take care, we need to consider the loading effect. So, that means, this resistance value should be much higher than the load resistance of the buck converter, DC-DC converter. And also we need to in many cases we need to match the impedance. So, you can put a unity gain buffer for the impedance matching, and then we take the feedback voltage, and this is where the error amplifier comes. In fact, the compensator in integrated circuit or even op amp, even the whole thing can be implemented using a single op amp. okay, or for sake of simplicity you can use multiple op amp, one for error amplifier and few more for let us say PID controller, but in general practical circuit like a type 2 type 3 compensator, one op amp should be sufficient, and then it goes to the comparator and there is a sawtooth waveform. Now, this PWM block which in fixed frequency it is we have already discussed. If we take a trailing edge modulation, what we found in the trailing edge modulation we have a sawtooth waveform, right. This is my sawtooth waveform and this control voltage which is the output of the controller is compared with the sawtooth voltage, and then the output is the gate signal, comparator output actually is passed through a latch circuit. So, this is my latch circuit, and this latch circuit is sync with our external switching clock, and this generate the gate signal for the converter. Okay. So, I want to consider a startup case study. That means, we have discussed already this trailing edge modulation. This is like a trailing edge modulation. This is a trailing edge modulation. We have or trailing edge PWM, because the switch turns on at the every rising of the switching clock that we have discussed, and switch turns off based on the comparator condition, this comparator condition. Okay. So, this condition actually decide when the switch should be turned off. Now, in voltage mode control, I want to show a startup case study. Okay. So, for the time being, let us consider a PID controller. In fact, I can tell you that a voltage mode control, typically people either use a PID controller or a type 3 compensator, which is like a lag lead compensator, and that we will take separately in the design of PID controller in the subsequent lecture. But today I want to consider a PID controller. The structure of a practical PID controller look like this: a proportional gain, integral and the derivative. So, generally we cannot implement an ideal derivative because we have a finite bandwidth limit of the op amp, and also we do not want to inject high frequency noise. So, we generally put a low pass filter, but this time constant should be sufficiently small so that we can retain the useful information. At the same time, we have to attenuate the noise. So, we want to implement the voltage mode control in MATLAB and we want to simulate a startup case study. Okay. So, I think we have to move before going to the MATLAB implementation. I want to show the MATLAB diagram. So, this converter diagram we have already shown, that means this converter was built up in the very beginning, like in the first week as well as in the second week. I have shown you that custom block to come up with this system or subsystem for the power stage buck converter, which include the parasitics of the switch, parasitic of the inductor, capacitor and switching signal. Now, we can take everything like input current, inductor current, capacitor voltage, output voltage, everything you can see. So, this model I am using, and this DCM enable is used whether you want a conventional buck converter or a synchronous buck converter. Okay. And here we can add an additionally constant current load separately along with a resistive load. Okay. So, in this block we are adding a new one, feedback block, which is like this is my PWM voltage mode control block. What is this? So, if we take this, that means this whole block is shown here. I mean, if you see this circuit, it is shown here, this particular circuit. First of all, we need a switching clock to turn on the switch, because we are talking about trailing edge PWM. We are talking about trailing edge PWM, and this is my reference voltage and the output voltage, and this is my error voltage. And I took here a standard PID controller, like a by default PID controller. I can separately implement this PID controller using a transfer function block from the MATLAB. I will show, already I have shown in the previous class. And this is a ramp, and the ramp I have chosen that ramp base value and the upper value I can customize, and this is compared, and the comparator output is used to reset the pulse, that means the turn of the switch. Okay. So, let us go to the MATLAB block and see that example. Okay. So, in this example we are going to consider PWM voltage mode control that I have shown you. So, in this diagram initially I want to show that this block I will discuss what is this. So, for the time being I will just keep this block separately, okay, because this block will be used in the subsequent slide. It has certain purpose. Okay, just 1 minute. Okay. So, I am using this block separately, but now I want to use a separate reference signal, and this is my Vref. And this is my Vref. That means, this is my reference voltage. Okay. So, the reference voltage is coming, and this block I have already shown the feedback block, and the gain of the controller are here assigned like a Kp, Ki, Kd, and which I am calling from the external MATLAB file. Okay. So, this is like a standard voltage mode control that I am going to discuss. Okay, I set some value Kp, Ki, Kd, and the upper limit of the sawtooth waveform is 10. That means, if I go here, this sawtooth waveform I set from 0 to Vm. That means, the base value is 0 and the upper value is V max, Vm, and its time is 0 to t time period. Okay. Okay. Now, with this let us simulate. What I am trying to do? I have enabled this PID controller from the very beginning, that means Kp 30, Ki 20,000 and Kd 0.04, and I am now running from the startup from the beginning. That means, it will ask for the initial condition. Let me start with the 0 initial condition and we will run it. So, if we run, I want to show you that. So, this shows the startup action, because this particular the top one is my inductor current, this is my inductor current, and this is my output voltage. So, you see the inductor current actually goes up to more than like close to 80 ampere, just because we are using a gain, maybe it is a large gain, and the voltage also going above 3 volt, like close to 3.5 before it coming to steady state, which is 1 volt. That means, such kind of huge current, it will simply it will burn the device, or it will damage the switches and the other because our ratings of the components are not designed. Okay. So, this is not desirable. In fact, the output voltage is too high, because this output voltage we want to regulate, and if the overshoot is too high, it can damage the application, because where we are using this regulated power supply. So, this is where actually I am showing this startup transient scenario in this presentation. That means, trailing edge modulation, I am simulating this startup transient, and this is what I have shown now. So, here I am using Kp, Ki, Kd, and you can see the huge transient. Now, the next question, how can I reduce this transient effect? That means, how can I so before I move to shape this startup action, we should also know what are the function of Kp, Ki, Kd, because we have used a PID controller, though we can change the gain, but generally I am talking about the analog controller, where the PID controller are set through external component. That means, they are set on at the very beginning of the converter. So, you have probably no choice or very hardly any choice to change this PID controller at the beginning, but we should know that the effect of Kp, Ki and Kd. If we increase the proportional gain, generally the percentage overshoot increases, or it is vice versa. If you reduce, it will get reduced. The settling time, it has minimum impact, but yes, of course, it has impact in the rise time. Higher Kp will reduce the rise time, but at the same time it will increase the overshoot. The steady state error can be decreased. The integral action is used to reduce the steady state error, and you can eventually go to 0 steady state error where limit is tends to infinity. But we generally set a criteria like a 2%, 5% error criteria to decide the settling time. Okay. Then if we increase Ki, then the percentage overshoot will also increase and settling time will also increase. So, it is not recommended to use a higher integral gain, and if we increase the derivative gain, we can reduce the percentage overshoot, we can reduce the settling time, and it has hardly any impact in the steady state error. That means, this does not play any considerable role in the steady state error, but it plays role in the damping. So, it will affect the overshoot as well as the settling time. Now, my next question, can I reduce the startup transient that we have discussed? Here I am showing a scenario. The red one, which was the original one, the number 1, which is like a without startup, and the blue one is the with startup. So, this is my with startup. What I am doing? So, in the first simulation, if I plot the Vref profile, that means I am just plotting my Vref. This is the reference voltage of the DC-DC converter with respect to time. In the first case, okay, so I am taking, in the first case we are taking the Vref straight away to its desired value. That means, this is the desired value, desired value. In the second case, what we are doing? We are modifying this Vref and then reaching steady state here. That means, we are putting something like a slew rate, and this time I will say T slew, T slew. Okay. So, what is my slew rate here? My slew rate will be equal to Vref by T slew. So, now earlier it is like we are suddenly applying the Vref at the beginning and the error was large, and that actually causes the whole overshoot undershoot, and which is not acceptable. But what we can do? We can now shape the reference voltage. That means, we can slowly increase the reference voltage till it reaches Vref, and the slope of this reference voltage change, which is like a ramp signal, that is user defined. Because if you want to make it very slow, then your converter will respond and you see there is no transient effect. So, in this case we have set how much? We have set 1 volt, which is Vref divided by 0.1 millisecond. So, this is the slew rate in our case. So, this is good, and you will hardly see any transient effect, but this may not be fast enough because we may want to speed up the response. So, we may try to increase this slew rate, and if we increase the slew rate, we will see the impact. But the next question, how can we implement this logic? That means, if we go to the MATLAB, now this is where actually I wanted to show. In the MATLAB, now instead of connecting this, I want to connect this now. Okay. What I did? Now, I add a saturation block because it is a ramp signal, and ramp is Vref by T slew. So, I am defining my Vref, and T slew is the duration, that is my T slew. So, Vref by T slew, but it will keep on increasing. We have to stop when the voltage reaches Vref, and that is why we put a saturation block. Upper limit is Vref, it cannot exceed beyond Vref. Okay. Now, we want to rerun this simulation and check what happen if we incorporate these changes. Okay. So, earlier it was the red color, now I want to make it like a blue. So, blue. So, I have not made any change in the controller, and we want to start from 0. So, here we put a very fast slew rate, that is why we would hardly see any. So, it is like a 0.1 microsecond, it is too fast. Okay. That means, it is same as originally, now we are putting 0.1 millisecond. Okay. So, now let us change it to green color and see the effect. Okay. That means, earlier we set a very high slew rate, even though we are putting that block, but we are putting a very high slew rate. Now, we are rerunning the simulation and see what happened. Thus, if the slew rate is too fast, then it is as good as that earlier, like we are putting a very fast VREF at the beginning. But now, you see we are putting a limit, that means we are setting a limit in the VREF, and now the voltage we want to change the voltage from 0 to 1. So, that means if we go for up to 0.1 second, you see the green color shows that voltage is increasing from 0 to 1 volt, 0 to 1 volt, yes, 0 to 1 volt in 0.1 millisecond, because it is in a millisecond scale. That means, we can achieve this soft start action from here. Okay. The next task, that means, you can change the slew rate. So, that means, MATLAB is slew rate, we have already explained that we can incorporate this particular block, and you can change the rate of the slew. Now, we are going for 2 loop control. Now, in 2 loop control, actually we have an inner loop, this is my inner loop, we have outer loop. So, this is a basic architecture of a 2 loop control, and where it is also called master slave control and cascade control, right. So, inner loop should be much faster than the outer loop in generally, and there should be a time scale separation. In fact, we will take the example of current mode control, and when we will discuss, there is a particular session where we want to discuss what will happen if 2 loops bandwidths are close to each other. So, what kind of interaction we will find, and such interaction what can it cause, that will also discuss. So, here in switch mode power converter, the 2 loop control outer loop are generally output voltage, inner loop can be inductor current, capacitor current, it can be the derivative of the output voltage, sometimes it is the ripple voltage, like in case of V square control. So, in current mode control, we have 2 loop control. So, this is my inner current loop, which is the inductor current loop, and this is my outer loop, this is my outer loop, and this is my inner loop. If we put a current sense amplifier gain or current loop gain, that is Kc, and this is a feedback gain for the voltage loop that we discussed, and then there is a voltage controller. Okay. So, I will show you the implementation of this block, and the alternatively, instead of an inductor current, we can also have a capacitor current control, in which instead of an inductor current, we can use a capacitor current, that is also possible. But it is very difficult to sense the capacitor current, because actually the capacitor current we should not put any resistance, extra resistance in order to sense current, because that can increase the ESR, and that may not be a that may be counterproductive in terms of the undershoot, magnitude of the undershoot, and so on, and that part also we will discuss when we talk about the output impedance. So, if we want to put any resistance in the capacitor, that can adversely affect the output impedance at high frequency, that we will also discuss. The another possibility, the inner current loop can be a derivative of the output voltage. That means, this can also carry the information of the capacitor current for a buck converter, but this may not be a good solution for a boost, where the voltage will have a non-minimum phase behavior. Okay. So, we have to be careful about this PID controller design, the inner derivative loop for boost converter, because it has a non-minimum phase behavior. Okay. So, derivative action, then we have, if we consider this, we can actually compare the response of the capacitor current with and the actual current mode control, we can compare. So, now first I am to show the MATLAB simulation of current mode control, and that we have already discussed. So, here now again I am introducing a controller here, and which is my current mode controller, and we want to see what is that, because these blocks are already known to you, and already these files are already discussed, the MATLAB file. Here this inside block, again we have error voltage, that means your reference voltage and the output voltage. Then although I am showing a PID controller, but typically for current mode control we can use a PI control or type 2 control, but in this PID controller we can keep the derivative term 0. So, that means we can realize using a PI controller, or you can use a separate transfer function block here. Now, this is our kind of a reference current, this is my reference current, okay? Or in this case it is my control voltage, and here it is a reference current which is compared with the inductor current. Now, if we consider, in the last class we discussed about the inductor current sensing, that means typically the inductor current is like a sense voltage equivalent to inductor current, and this sense voltage is related to the current linearly with a scaling factor of a R equivalent, and this R equivalent magnitude depends on if you use any sense resistor or including the current sense amplifier gain. So, here I am just showing the basic structure of a current mode control, where inductor current is directly compared with the reference current, and reference current is the output of the compensator. And this structure remains same because it is a trailing edge modulation. Okay. So, this I want to show you the current mode control implementation. So, this was our voltage mode control. Okay. So, if we go to current mode control, in current mode control, this is what the block diagram I was showing. Okay. So, we can now, let me maybe 80 or something. So, this saturation block may be there, may not be there, because this is my peak reference current, and this peak reference current we can put a limit on the peak current, because it is a peak current mode control, and we can always put a limit on the peak current. That is why I am putting a saturation block, and since the current can go in the either direction, that means there can be overshoot, undershoot in the current. So, this saturation block should allow the limit in the either direction. So, initially I put a very large limit, so that actually the current will not get saturated, that means the controller will not get saturated, and it is compared with the inductor current. Now, I want to simulate this. Okay. So, I want to simulate. So, I will open this current mode control simulation file. So, what I am doing here I took the PD controller to be 0, derivative controller to be 0, it is just a PI controller. Here I do not need to put any slew rate limit, because I do not need any external switch. Why I am saying? Because I use a simple VREF, but I still want to see, can I implement such soft start logic in current mode control, what we did in voltage mode, without modifying the reference voltage, which we did in case of voltage mode control. Okay. So, in this case, if I run again the start, that means we are starting, yes. So, if we, this is the startup, the top one is the inductor current and the bottom one is the output voltage. Okay. So, you will find the output voltage reaches 1 volt much faster, that kind of within like a 0.025 millisecond, that means 25 microsecond. But there is also a huge peak current, okay, and that may not be acceptable, it may exceed the rating of the device. Now, this goes back to, but it is much better than voltage mode control, because we have a direct control over the current. Now, the next question, we want to set a current limit and see how can we improve this startup performance without violating the current limit. The question is, what value of current limit should we set? Again, it depends on, we discuss about the power stage design, and when we came up with the power stage design, we identified the peak current depends on what is my maximum load current. So, in this case we consider 20 ampere, so we can go up to 25 to 30 ampere. So, here I am setting, let us say 20 ampere current, even or 25 ampere current. So, if I set a current limit of 25 ampere and the same value I set like a minus side also, minus 25 ampere. So, now I am putting a current limit, okay, and I want to repeat the same simulation, but now with a different color, okay. So, I am not changing anything, there is no additional soft start circuit, but what I am doing here, I am just repeating the simulation with a current limit. Okay, so, I put a current limit of 25 ampere both upper side and lower side and see whether can we, yes, you will find still the current is limited within 25 ampere, like it is nice that it is not exceeding 25, but there is a voltage overshoot which may not be also acceptable, because it is going around 1.1 volt. So, let us say if you are talking about a power supply for a processor, that 100 millivolt may be too high. So, we have to limit this. That means, at the beginning we can set the current limit to maybe 20 ampere, and if you set to 20 ampere for both up and down, and we want to see what is the impact. That means, I want to repeat again this simulation. Now, I will use a green color and see. Okay. So, now what I did, I just put a current limit, in fact, there is a closed feedback loop. So, there is no problem, and I have decreased the current limit from 25 ampere to 20 ampere, and this is my response. So, now you can see the startup performance is significantly improved. Okay. So, I can set the peak current limit up to the nominal load current. Okay. Okay. So, now here we do not need. So, what I am trying to mean here, I am taking 2 loop control, and in 2 loop control the startup can be taken care inherently by the controller itself. So, you do not need a separate startup logic which was there in case of a voltage mode control. Okay. So, by using the current limit we can actually make a kind of a soft start. At the same time we can actually take the benefit of fast slew rate, because the voltage slew rate will be much faster, and we have a comparative study here to show. That means, for current mode control this is without any peak current limit, and this is a 20 ampere current limit, and it is a very nicely reaching its final value without like a overshoot, voltage overshoot, and the current is also limited to 20 ampere. Now, if I want to compare the startup logic between voltage mode control and current mode control, so you will see in current voltage mode control, though the current overshoot has reduced during the startup, but the slew rate of the output voltage is much slower, and this can affect, that means your because you want to really speed up the startup process. So, since we have designed the converter, the component based on the maximum current rating, so 20 ampere current limit is much within the limit. So, why can't we go up to that point and speed up the response rather than we limit the current to a very lower value. So, that means I would say this current mode control startup process can significantly improve or save the startup recovery time. That means, in single loop control, no control over current, because there we have to limit the slew rate, because we have no control over the current, though in most of the IC the protection current sensors are used for protection purpose. So, we can take the advantage and to implement this current based logic for the startup, but in typical voltage mode control there is no control over current. The compensation is sensitive to operating condition. This part we will highlight in the design of buck converter voltage mode control, DC-DC converter voltage mode control, but the fault protection and the startup logics are separately needed. That means, we need to separately incorporate this startup logic in voltage mode control, where we want to slowly increase the reference voltage. So, you need an additional circuitry to do that, and if there is a fault, that means the current can simply kind of damage the switches and the other device. That is why for the fault protection purpose we need to put a current sensor, and the startup transient is difficult to optimize. Whereas, in 2 loop control we can reduce, first of all this part we will discuss, because in 2 loop control we have an inner loop and outer loop, and we want to make sure the 2 loops are widely separated in terms of their time constant, but by virtue of this inner loop and outer loop concept, we can actually represent this converter to a first order approximate system. So, that means, and we can, and this will simplify the design process. Okay. The higher bandwidth can be achieved because we are taking the advantage of the fast inner current loop, but it require everything comes with a price. So, the sensor requirement, and in current based implementation we need a current sensor, and also there will be, I will also show the subharmonic instability in current mode control when the duty ratio exceed 50% for peak current mode control, and we need to separately incorporate the compensating RAM. Okay. But in digital control and other modulation technique, this problem can be resolved, that we will also discuss. And now using digital control implementation, we can estimate current, even we can estimate really very fast dynamics current. So, we can get the benefit of faster current loop without sensing current. Those are possibilities. So, with this today I want to summarize that fixed frequency single loop controls are discussed, two loop control method discussed, then MATLAB based implementations are demonstrated, and advantage and limitation of feedback control methods are also discussed. And we will see more detail about single loop and two loop control design in a subsequent lecture. But today I want to give a glimpse of the feedback control and their implementation in MATLAB. With this, I want to finish it here. Thank you very much.